Hey everyone and welcome back to PrepFusion. I am Anish and today we'll start a new chapter that is electromagnetism. So we have covered about electric fields, we have covered about electrostatics. So now in today's lecture we'll study about magnetism. We'll study about magnetic field characteristics, okay? And also we'll learn about Biot-Savart's law. It's just like same as Coulomb's law. We'll learn about what is Biot-Savart's law, but here we'll not talk about force. We'll talk about the magnetic field only. Okay, and what is magnetic field is similar to electric field only. Okay, so we'll learn about that. And in what I will tell you is what I will recommend you. Electrostatics is a very big chapter. Okay, and questions like the weightage of electrostatics will be more than electromagnetism. So you should play, like, if I just want to give you an analogy, right, you should play electrostatics as a test match because it is very lengthy and it has many things and it is very conceptual. And and magnetostatics, right, you should play as a ODI or T20 match. Why? Because many things will be related to electrostatics. Obviously things will be different here, but many things will be related. So I will go a bit fast over here. And weightage wise also it's like not too high. Okay, mainly questions come from electrostatic, but this is obviously important if you want to get a good rank. Obviously every topic is important, right? So we'll cover everything conceptually, but we'll cover fast. Okay, we'll not study everything slowly because few basic fundamental knowledge has been cleared from you with the help of chapter 2. Now we'll study the chapter 3, magnetism, okay, or magnetostatics. Okay, so what is magnetism basically? So first of all, how we identified this phenomenon. So there was one person named Oersted, okay, and he performed a experiment. Okay, he saw that when moving charges or electric current produces a magnetic field. Like he observed this thing that when I move charges or that when electric current flows through a particular wire or some place, right, it produces a magnetic field. Now here and like how we get to know about this. So if you observe that a particular device known as compass. So if you move the compass at different places of the earth, you will see the compass deflecting. The orientation of compass needle changes around a current carrying wire, indicating the presence of a magnetic field. Okay, if changes, if I move around earth, the orientation of compass will change, right? If I move around, now if I take that same compass near current carrying wire, right, what I will observe, the needle will deflect. Why is the needle deflecting? So needle has some force has been applied to the needle, right, to deflect it. So there must be something else that is producing that deflection. That deflection is basically the magnetic field. Like in Earth's magnetic field, if you know already, Earth has North Pole and South Pole, and its magnetic field is something like this, right? If you know about this, but obviously it is very weak, not that strong, because the body itself is very big, right, and it covers a whole huge area. And like this was the experiment that I was talking about here. Like I have a I have a bulb, and I have a galvanometer here, and if I just close the circuit, this galvanometer will deflect. This concept we learn about in the measuring instruments, that why is this galvanometer deflecting? Due to magnetic fields, because inside we have used the principle of electromagnetic induction that we learn in measurements. Okay, but this is one basic thing. But what did Oersted did? Okay, I will read here. The Oersted experiment was conducted by Danish physicist Hans Christian Oersted in 1820. The experiment demonstrated that an electrical current in a wire produces a magnetic field around it. So it was a special experiment that he demonstrated, and it has shown that if I produce, like if a current flows through a wire, and if I observe the magnetic fields, it will provide a magnetic field like this. Okay, so it will provide a magnetic field like this. I will discuss about this more later on, don't worry about this. But what we are interested in currently, we are interested in the magnetostatics portion. So what is magnetostatics? Magnetostatics is the study of static magnetic fields, which are fields that do not vary with time but may vary with space. I hope you know the difference between time and space. This has been covered in electrostatics. So here mainly we're concerned that in the next chapter we will study about field that varies with time as well. But for now, in this chapter, our fields will not vary with time. Our fields will only vary with space. That is, if I am at this particular point, my field will be something else, some function of x, y, z. If I am at this point, my field will be something else, function of x, y, z. Most cases it will be uniform. This and this field will be same. Okay, but it can change as well. That also I will derive. Okay, that thing is one thing. And what are the few magnetic field characteristics? So first magnetic field characteristics is that magnetic field lines exist in closed loop and have no starting or ending points. What does it mean? So in electrostatics, right, what we learned is from positive charge, electric field always goes radially outward. Okay, it acts as a source, and negative charge, all the charges come radially inward towards it. It acts as a sink. But in magnetic field, there is no source or sink. No source, no source or sink. Okay. So if it doesn't have any source or sink, what does it mean? Just hold on a second. I will just not show the touches actually. That is, yeah, sorry for the interruption. I was actually turning off one this show touches thing. So here it will not have any source or sink. It will exist together. So if you observe one thing about magnetic field, that if there is a north pole, just hold on, if there is a north pole, then there will be a south pole. Okay, a north pole cannot exist on isolation. This is the special thing about magnetic fields. Okay, in electric field, positive charge can exist separately and negative charge can exist separately. But here, if north pole exists, there has to be a south pole of it. Okay, and through these characteristics, what is the mathematical mathematical relation? What is the mathematical relation? So if north and south pole will exist always together, so I will write here that my north and south pole will coexist, always coexist together. If they always coexist together, right, I will come to this in the next slide. If they always coexist together, now just one thing I wanted to say. If you recall anything about electric flux, right, electric flux, what was the definition of electric flux? It was basically the flux that flows through a particular surface. Now if I take any closed surface, what will I observe is that as it doesn't have any source or sink, the amount of flux whatever comes in, it will always, the same amount of flux will go out. That is the fundamental characteristics of magnetic field. So through this we get our fundamental relation that is written in the next slide itself, magnetic field always exists in a closed path. That is, it originates and terminates at same point. Okay, it cannot exist, like it always has to exist in closed path. Why? Because if this magnetic field line has went out, right, it will again come back and join this path. As it is existing in closed path, what will happen? If I find out the flux, right, it will go and then come back from the same surface. Okay, whatever surface you want to take, you can take, but that is a fundamental characteristics of magnetic field. So through this I can directly write this relationship that my magnetic field will be solenoidal. It is also called as solenoidal, and with B, magnetic field is generally denoted with B. So it del dot V, the divergence of magnetic field as it is solenoidal, will be simply 0. Okay, this will be always the case. This condition is that's why magnetic field is called as solenoidal field. Okay, same as if you recall something, it's similar to this relationship, right? As electric field was e-rotational, del cross E was e-rotational, as electric field was conservative in nature, because if I go and come back in the same point, it will be 0. Del cross E was e-rotational, it doesn't have any rotational effect to it. Same as magnetic field doesn't have any source or sink. Okay, the similarities I'm going through both of these fields. Okay, I hope you understand. Then let's read the second point. What is the second point? Magnetic field lines never intersect with each other. Magnetic field lines will never intersect with each other. Same as electric field lines, right? Why? Because here if I observe, let's say I have a magnetic field here and magnetic field like this. Okay, this and this. Okay, if both of the magnetic fields are here and here, then what will happen? Basically at this particular point, right? At this particular point, I am telling you that magnetic field can be this point as well, which is not possible. It's not possible. Like in a magnetic field, there can be only one direction along its tangent, right? So obviously there will be only one direction. That's why magnetic field lines will never intersect each other. This is the fundamental property. And let's see through a current carrying conductor how is the magnetic field. So how do you calculate the magnetic field? Okay, so basically if a current is flowing, right, what I do is I use my thumb on the direction of my current. I will as the current is upwards, I will project my thumb upwards, right hand thumb. Okay, right hand. You should do it with the right hand only. Whatever we'll do everything with right hand. We'll not use any left hand. Okay, so if you are lefty, please go back and use your right hand. So if I project my thumb upward, then what I do, curl my fingers, right, just curl my fingers, okay, towards my give a thumbs up, then the direction of this other fingers, right, gives the direction of the magnetic field. So here if I observe that if I just project my thumb upwards and the fingers will curl something like this, right, so obviously the magnetic field will be something like this, and obviously it will never intersect. Okay, although magnetic field we cannot see it, it's invisible, but magnetic field is present everywhere. It's currently present. Earth's magnetic field is always present. Okay, just like electric field, can we see electric field? No, but it is present. Same as magnetic field, it will be present, and its direction will be something like this, as explained with the right hand rule. Don't worry, I will go more in depth with the right hand rule in the next few slides. Just I am giving you a brief overview of magnetic fields and what are magnetic fields basically. So this point I hope you got clear, that magnetic field always exists in a closed path. It originates and terminates at the same point. So if it has originated here, then it will terminate here as well, same point, right? So like this north south is very small. Okay, now current conductor produces a magnetic field similar to that of a bar magnet, affecting nearby materials like iron filings. So this was found out by Oester's experiment, and this is what we observe, that if I hope you know bar magnet actually produces a magnetic field. Okay, and if a current conductor is there, it will be similar to a bar magnet. So we can use current conductor to replace a bar magnet, and we can do some special things that also I will explain later on. Okay, now few basic things about magnetic fields is that attraction and repulsion. Obviously opposite poles north and south will attract each other, while like poles north and north will repel each other. Same like electric field, right? Same charges, positive charges repel each other, opposite charges attract each other. Positive negative attract, positive repel, negative repel, just like here as well. So if I observe in this particular scenario, right, let's say I have two bar magnets. What will happen is that as there is a north south here, okay, so this magnetic fields will terminate from here and originate at the south. Okay, and this south will terminate from this north as well, and from this north as well. Few field lines will flow here as well. Okay, and here if both north are present, okay, if both north are present, then what will happen? Magnetic field lines will not get attracted here. Magnetic field lines will get repelled. Okay, they will get repelled to the other end. Okay, now these are the magnetic field lines. How the magnetic field lines behave in presence of a few bar magnets that I have shown. Now you might say, sir, what if I just have a south pole over here? I will say it is not possible. Okay, I will say it is not possible. You can never have a single south pole. You will with a south pole you will always have a north pole. Okay, with a south you will always have a north. Okay, you cannot have just a south. Okay, I hope this point is clear. So with the help of this concept, let's try to solve a gate POIQ. Okay, so I have just shown you 3-4 slides right now, and can we solve a gate POIQ with whatever concept we learned about magnetic fields? Let's try to do that. The magnetic flux density. What is magnetic flux density? Just it is same as electric flux density. Okay, that's the magnetic flux density, and I have already told you, right, this B thing is magnetic flux density only. I will come to this. Don't worry. I will define this in a more better way. This is just telling me what the number of field lines in a area. The density of field lines, magnetic field lines in a particular area is known as the magnetic flux density. Don't worry, I will come to this. It's Weber per meter square. This unit also will come. The value of the K constant must be. What is the value of the K if this is a magnetic flux density of a given space point? What have I told you? What is the characteristics of magnetic field? It is source free. So not source free. It doesn't exist individually. So it doesn't have any source or sink. Okay, it doesn't have any source or sink. Okay, so it will originate and terminate at the same point. What does it mean? It means the divergence of the magnetic field will be 0. So if I find out the divergence, it should be equals to 0 of this magnetic field. So I will just do that. So if I try to do this, del dot B, if it is a magnetic field, for a magnetic field, for a valid magnetic field, what needs to happen? Basically, the divergence of that particular field must be 0, right? So I will just do that same. I will find out the divergence of the magnetic field. It will be 4 plus 2k plus 0 must be equals to 0. So from here we can get that my k is equals to minus 2. So k is minus 2 basically, which is option A. So it's like this was just the first question and we simply solved it. We just made the divergence equals to 0 and k, we find out the value. So in electromagnetism, right, simple questions will mainly come, not the difficult questions. So we will be able to blaze through this very well. But electrostat, I agree, it's very difficult. That's why I went very in depth to that, and I hope you enjoyed the electrostat. Okay, so now let's understand that about the direction. So I've just briefly explained about direction. Now let's formally understand about it. So we will find out the direction of magnetic field with the help of right hand thumb rule. So to determine the direction of the magnetic field around a current carrying conductor, use the right hand thumb rule. Point your finger in the direction of the current. Okay, point your finger in the direction of the current, that is point your thumb. Okay, point your, sorry, not finger, point your thumb in the direction of the current. Then the curl of your fingers around the conductor will indicate the direction of the magnetic field. If I curl my fingers around the conductor, okay, this conductor, that will indicate the direction of the magnetic field. It will be just like a concentric circles. Okay, so this was about the direction, and I hope you know about this. And what magnetic field, like how do you define magnetic field lines? We define it by magnetic flux density. Okay, B, this is known as the magnetic flux density. Now what do I mean by magnetic flux density? Magnetic flux density basically means the concentration of magnetic field lines within a particular area or within that small region. Okay, so just giving you a brief definition. Density of magnetic field lines within a region. Okay, same as electric flux density, same as that. And there will be another term known as magnetic field intensity. Okay, again it will be related with a constant, same as electric field intensity. Okay, so just remember few key points you have to remember, that this thing works only for right hand. Okay, it will not work for left hand, and we will not use any left hand convention to stay away from confusion. Okay, so if you are lefty, as I explained previously as well, you have to use your right hand. What is the other thing? Another thing is, as current is not a vector quantity, we choose another element. We'll choose another element. We'll choose a vector quantity dl. Okay, and that dl will be in the direction of current itself. Okay, and it will be a vector. As current is a tensor quantity, it is not a vector quantity, so we cannot choose current as a vector because vectors are required. So we'll choose dl. That is the reasoning behind choosing a dl, to find out the direction of the current. Okay, that's it. That's only the thing I wanted to explain. Now we'll come to Biot-Savart's law. So there were actually two people. Okay, so that's why the law came, Biot-Savart law. So the Biot-Savart law describes a magnetic field created by a small segment of a current carrying conductor. So if I have a very small segment, right, of a current carrying conductor, and current is flowing like this, okay, so the dl will be this, and dl direction will be in this direction only, along the direction of the current. And Biot and Savart, there were two people who derived the expression. So Biot and Savart told me that for a small current carrying conductor, a magnetic field will be produced dB by this small segment. How much will be the magnetic field? That magnetic field will depend on the magnitude of the current, will depend on the direction of the dl vector, and also will depend on the this angle. Okay, will depend on the sine of this angle. Sine of the angle between what? angle between here. Obviously it depends on the distance as well. Okay, it depends on the distance as well. So here, what is the angle? Let's say I'm trying to find out the magnetic field at this point P. If I'm trying to find the magnetic field at this point P due to this small dn, right? So this distance is, let's say, r. So there is some angle between this line coming outward from this wire to this point. What is the angle? That angle is this, right? Theta. So Biot and Savart both actually together come to a conclusion that my small magnetic field produced due to this small element dl will be proportional to, obviously, first of all, the magnitude of the current. It has to be, if current is more, I will get more magnetic field, more denser field lines. It is proportional to dl, obviously. It has to be proportional to the dl thing, okay, along the length. So basically, it is also proportional to the sine of the angle. Basically, I can say sine, right? Sine of the angle between this vector and this dl vector, right? The angle of sine of angle between them. And what else is it proportional to? It is proportional to the square of the distance, inverse square of the distance, basically, because that is understandable, right? That as the distance increases, if I keep on increasing the distance, the magnetic field will be weaker. If you go away from something, right, that person becomes weaker, right? The force developed due to that becomes weaker, just like gravitational, if you remember, inverse coil. Okay, so all these things are there. So Biot-Savart law actually put on a formula with all these things. Okay, before going in that, I want to share a few things. Thing one is this ideal. Okay, so what is ideal? Ideal actually is known as the current element, small current element, and we will use this in a lot of places. Why we do this? Just to give a direction to current. Okay, because current in itself is not a vector quantity. Just to give a direction to current, we use this ideal current element. Okay, just trying to understand the direction. And what is theta? Explain everything here perfectly. Theta is the angle between the angle between the r vector coming radially outwards and the dl vector. Okay, angle, just write it better. Angle between r and dl vector. Okay, so here, right, this is the scalar form of Biot-Savart's law, because the magnetic field is related with all of these things together. If I combine all of this, there has to be a constant, and that constant is known as mu by 4 pi. That constant we write mu by 4 pi. Why you will say mu by 4 pi? Why not simply mu? There is a reason for it that I will explain later on. Don't worry about it. Okay, so this will be the formula for the magnetic field produced due to a small current element. Okay, small current element. That's why we take it current element. Current element is this quantity. Okay, so ideal. This thing is only valid for current element, and this is the scalar form basically. Okay, scalar form of Biot-Savart's law. And we define the units now. We'll define the units. The units is Tesla. The unit for magnetic flux density is simply Tesla. Okay, so this is the unit, and this you have to learn. And other way also we can derive Tesla is also equals to Weber per meter square, as it is density, and flux's unit for magnetic flux unit is Weber. And if I derive it further, it will be divided by area, so it will be Weber per meter square. Okay, so Tesla can also be written as Weber per meter square. This is also another unit for magnetic field intensity. So there is one term, like this is the simple expression, scalar expression. I will talk about the vector expression as well. Don't worry about that. Okay, scalar expression is this, and there is a mu term, so we will talk about this mu term now. All these terms I have already explained. You got, this is the distance, this is the ideal current element, this is the angle between the dl and r vector, and this thing is fine. So mu is simple equals to mu naught mu r, and mu naught is the standard permeability, also known as, this is known as the magnetic permeability. Mu naught is the magnetic permeability of vacuum or earth, and mu r is the relative permeability, same as the dielectric constant or permittivity. Okay, so what is magnetic permeability? The permeability of a material is a measure of its ability to allow the passage of a magnetic field through it, same as the dielectric permittivity. How much magnetic field can it pass through? How much is the ability? So that is simply a constant. For free space, this constant permeability is given by this: mu naught by 4 pi equals to 10 raised to power minus 7 Tesla meter per ampere. So you can just derive the units from this thing, right? You know the units of Tesla, units of magnetic field, and ideal, sin theta, all these units you know, and if you derive all those units, you will get back these units. Okay, so better way to remember mu naught, like this is the one way to remember that mu naught by 4 pi is 10 raised to power minus 7 Tesla meter per ampere. This is in SI units. Okay, this is in SI units. So better way to remember will be this: mu naught will be equals to 4 pi into 10 raised to power minus 7 Tesla meter ampere. Okay, so this is how you can remember. And mu is equals to simply mu naught into mu r, that we already know. This free space means vacuum or air as well. Vacuum or air. Okay, so few important terms that I wanted to talk about. Okay, this same analogy to our electrostatics is the magnetic flux density. This is denoted by B. Magnetic flux density, yeah, it's denoted by B, and its unit is what? Weber per meter square. This is the unit of flux. Okay, so this, can I relate with this with the electrostatic? Yes. Remember, there was a D, electric flux density. Its unit was coulomb per meter square. Okay, so this unit, this unit will be simply Weber per meter square. Weber is the unit of amount of flux. Okay, and there coulomb was unit of amount of charge. Now, what is magnetic field intensity? Magnetic field intensity is just related with magnetic flux density. And how is it related? So here things are a bit different. Okay, don't worry about it. But we know everything, right? We know everything. So here what will happen? I have to actually why we like derive another term, electric flux density there. I wanted to derive another term to get rid of the constant, that electric permittivity that was there, right? I wanted to get rid of it. So if I want to get rid of this constant, right, through this dV, what I will do? I will divide by mu naught on both sides, right? I'll divide by mu naught on both sides. If I divide by mu naught on both sides, that will basically give me the electric field intensity, which will be independent of mu naught, which will be independent of medium. So I want to get a term independent of medium. So this term will be independent of medium. So if I need this term to be independent of medium, what I will do? I will divide my magnetic flux density divided by mu. Okay, that will be equals to my H simply. Or in other ways, what I can say that my B is equals to mu times H. Correct? Just same relationship as what? Same relationship as my D was equals to epsilon E. I had to remove the epsilon from the bottom, right? So if I multiply epsilon with it, so that will get removed. So it will become a medium independent term, and that is exactly what is happening. Okay, so I hope you can derive the units for magnetic field intensity from this particular thing, from this particular exercise. And what will be the unit for magnetic permeability? I have already defined the units here. This also can be written as Henry per meter. That we'll study later on. Don't worry about this. Henry will study later on about inductance and all those things. Okay, so here, like, I have written a few text about magnetic flux density. You can read out all these things. Basically describes the influence of current carrying conductor in its surrounding, represent as B the number of magnetic field lines per unit area passing normally. This is important. Normally through the surface is called magnetic flux density. Same as electric flux density. Passing of electric flux normally through that area. Now magnetic field intensity will be simply, the magnetic field intensity is a measure of the strength and direction of the magnetic field at a particular point. Okay, just it is medium independent. That's it. This term is medium independent. This term is medium dependent. Okay, that's why we derive it like this. We need a few terms like this while explaining the boundary conditions. Now we'll come to the Biot-Savart's law vector format. Okay, Now I know the magnitude Biot Savart has given me, but how do I find out the vector? Because this time vectors are a bit difficult. It's not simple dot product anymore. Why? Because what I'm observing is due to this current element, right? What will be the direction of magnetic field? So how you used to find out the direction of magnetic field? Just point your thumb towards the direction of the current, and then what you should do? Then basically what you should do was simply you curled your fingers towards the point P, right? Towards the point P, you curled your fingers. So if I just curled my fingers towards the point P, what I will observing, it is going into the board. Okay, going into the board, going into the skin. So this at point P. And how do you define going in and out of the screen? So this point is very important. So just quickly draw this thing. Okay, so this is coming out of the skin, and this is coming into the skin. Okay, so this is in and this is out. In means arrow is going out. Okay, if a arrow is there, and behind the arrow there is shape like this, right? Arrow shape are like this, right? So if arrow is going away from towards you, going into the board, what will you say? You will just see that behind thing, right? The behind thing of it, which has a cross sign like that. So that's why if it is going in, we denote it with a cross, and if it is coming towards you, right, you will just see the tip of the arrow. Just see the tip, and tip is very small point. So you will see a point coming towards you. That's why it's out. Okay, so in the case of P, what are you observing? It is going into the, if I just place my thumb and curl my fingers towards it, okay, place my thumb and curl my fingers towards it is going into, right, it is going into the point P. Place your thumb and just curl your fingers, right, curl your fingers in the P. Okay, so place your thumb and curl your fingers, so it will be going into the plane. Okay, dB will be into the plane of V. So in this case it will be in, it will not be out. Okay, sometimes it can be out as well. So if my P point is lying somewhere around here, lying somewhere around here, so now if I point my thumb and curl my fingers towards P, what I am observing, it is coming in towards me, right? That curl is coming towards me, so it is coming out of the plane. Okay, so like all that is fine. Okay, doing all this is fine, but how do you write this mathematically? So what we identified was that the direction will always be a vector that will be perpendicular to both DL and this R vector. Okay, I will get a vector that will be always perpendicular to DL and R, and when we get a vector that is always perpendicular to two vectors, what I do, we just simply apply the cross product of those two vectors and we'll get the direction. So exactly same thing I'm doing the cross product with the current element and the position vector of the point P, and through that I will simply find out the direction if I just do the cross product of these two things. Okay, I hope you understand. What is the position vector? Final minus initial due to this point, and final is this point. Okay, so position vector is of point P, where magnetic field, this should be here, is to be calculated with respect to current element. So I hope you understand how do you calculate position vector. All these things we have like explained multiple times in our electrostatics chapter. Okay, so I hope now you understand this thing. Now, like, it's a simple exercise for you, just a simple exercise. Tell me, if this point is P, you already know about P. If this point is P dash, although I have explained this, I wanted to see how, if you are listening to the lecture or not. So this is P dash and this is P. Can you tell me the direction of the magnetic field? Okay, with inwards or outwards, whether it is inwards going into the plane or going out of the plane, going out of the screen or coming in, going to the screen. So for P dash, I can observe if current is flowing, just hold on, if current is flowing like this, right? If I just curl my fingers, I will see at this P point it is going into the plane, so it will be a cross sign, right? It will simply a cross sign. And at P dash point it is coming out of the plane, so it will be simply a dot sign. So this type of convention you have to keep in mind. Okay, so these are few simple things only that I wanted to say. So now we will do few questions, and with the help of that our concepts will get more clear. So like I will derive the formula as well, I can derive the formula as well, but for now like through this questions only I will derive the formula. Okay, what will the formula? A wire carrying a steady state current of 50 ampere as shown. Okay, both these wires are carrying this current. Determine the magnetic field produced by a small segment, by a small 1 centimeter segment of this wire at a point located 1 meter away. Okay, so this point P1 and P2 are located 1 meter away. Okay, and I have to find out the magnetic field for the two cases. So along with direction. So for a small segment, this is 1 centimeter, is very, very small segment. This, let's assume this is an infinite wire. Okay, so what I can do, I can simply say the solution of this. Okay, can write down the solution here for the case 1. Okay, for the case 1 I will just copy the diagram. Okay, if I copy the diagram, and like you already know the direction. What is the direction? Direction is, if I just take a cylinder, right? If I just take a cylinder, direction will be along aero cap direction, right? It will be along aero cap direction. So I will take cylindrical coordinate system. Okay, and I can say that my DL, if I take cylindrical coordinate system, right? I will just show you here. XYZ is something like this. X, Y, Z. Okay, so it will be cylindrical coordinate system. So what will happen is, just hold on. Why is it not working? Yeah, so what I can say, what is the direction of my current element? Ideal direction will be, it will be I dl magnitude Az cap. Okay, and dl is very small, that is 1 centimeter. Okay, very small length. So this small electric field I can say will be, what is the formula? It was mu by 4 pi was there already, that is mu naught by 4 pi. That's fine, as nothing is mentioned, they haven't mentioned anything, so I'll assume it has free space. So I'll assume it has mu naught into ideal Az is there cross this vector. What is this vector? This vector, right, is simply aero cap. Okay, this is aero cap because this is 1 meter. This is 1 meter only. So this is simply aero cap, right? In the aero cap direction. I'm just using cylindrical coordinate system. So this is in the aero cap direction. And that's it basically. What was the formula? Divided by the distance, r square. It is 1 whole square, right? So this was the form, right? It was dB was equals to I mu by 4 pi into IDL cross r divided by the by the, like this r vector cross r is the direction basically, divided by the magnitude of r square, right? If you remember here in the vector format, I just skipped one thing. This was supposed to give me the direction. Okay, because here okay, I just skipped one thing here. Because here if you observe, I just derived this without, like this, what was this ideal sine theta? This ideal sine theta was supposed to give me just the direction. Okay, if you observe, this ideal sine theta is what is the component of current that is totally what do you say, contributing to the magnetic field. What is the total component of the current that is contributing to the magnetic field? Because if you observe one thing, if the current is flowing like this, right, it will not contribute any magnetic field here. If the current is flowing directly perpendicular, it will contribute to the magnetic field. So this sine theta was present. The reason of this sine theta was simply the perpendicular component of the current. Okay, perpendicular component of current. Now here, like I just skipped few terms here over here. This term, right? This term was like previously this r cap distance was not there. Okay, so what I did, I just computed dl cross r vector. What happened? If I computed dl cross r vector, right, an extra r magnitude is at the top, so I had to reduce that because I don't want that extra r magnitude. It was totally depending on that ideal sine theta only. Okay, so what I did, I did dl cross r. An extra magnitude of r is at the top, so I will divide by magnitude of r. Previously it was r square, now it will become r cube. Okay, what I did was, if I do this, just dl cross AR cap, okay, and I will keep this as magnitude of r square. That is fine, because an extra magnitude is not getting multiplied here. Just simple one, magnitude of AR cap is 1, but here if I do dl cross r vector, the extra magnitude of r vector is at the top, which is getting multiplied, which I don't want. Basically my relationship was only this, okay, it was not this extra term. I did this just to find out the direction and just to find out the perpendicular component of the current, because what is the, if you break this down, what is it, what is the breakdown of this? Dl r dl sin theta, magnitude something perpendicular to both of the planes, right? If you remember the cross product definition. So obviously to do that I had to divide by extra q here, but I already know the direction of this particular r cap, that is unit vector, that is a rho cap, okay. So it's already easier for me. So this will be equals to what? Mu naught is how much? Mu naught is 10 raised to power minus 7, 4 pi into 10 raised to power minus 7, so this will become 10 raised to power minus 7. Have they given us I is 50 amperes, okay, they have given us 50 amperes. And what is the small length dl? They have given us a small length dl, that is 1 centimeter. So 1 meter is very far away than 1 centimeter, but so that this length is very small in comparison to the distance. So I can write directly here, I will replace directly here 1 centimeter. And what is AZ cross arrow? So if you ever tend to forget about these things, right, like obviously you can identify this by with logic. Simply if I do AZ, I will point my fingers upward and then I will curl my fingers, it is going inwards, so it is on the direction of arrow cap. But if you want to do it other way around, you can do it other way around as well. How? You can simply remember this, right? I hope you remember. For AX, AY, AZ, you remember AX, AY and AZ. Okay. This needs to go at the bottom, top, and this needs to go here. And if like this is for the Cartesian coordinate system, what about the cylindrical coordinate system? I have arrow, then a phi, then az, and then arrow, correct? So if I have arrow, then if I do a cross arrow, I will get a phi, and so I will do if I do az cross arrow, I will get a phi. So I am doing az cross arrow, I will get a phi. So here I will write a phi. So this will be the direction of the magnetic field, basically on the a phi direction. And if I just further simplify this, this is 10 raised to power minus 6, 10 raised to power minus 8. So 5 into 10 raised to power minus 8 in the arrow cap direction. And what is the unit? I hope you remember the unit. Unit was simply Tesla, or wave per meter square also you can write. I will write this like I can further simplify it as 50 nano Tesla, okay, in the a row cap direction, or you can say that it is going inwards to the screen. Okay, if I can draw the shape inwards to the screen, right? If I can somehow draw the shape. Why? Because if I observe from the, if I just use my right hand, I will point the current direction with thumb and then will curl my fingers towards the point. If I am observing it is going into the skin, if it is going into the skin, obviously that will be the sign for going into the skin. So now let's do it for the second question. So for this first question, right, what caveat I wanted to give is actually for this question to be more proper, we should have been given exactly where this wire is located and location of this point P. They have not given us. So I assume, okay, this is the y. I will assume that this is on the x equals to y equals to 0 along the z axis. Okay, and this point is also just on the perpendicular to the z axis. Okay. So one more thing I forgot to mention is that, like here when I told you, right, when I told you that it is ideal sin theta, another reasoning for this sin theta is what? Perpendicular component of the current or the perpendicular distance. Okay, this perpendicular component of current also I can say, or the perpendicular distance to that point. Perpendicular distance. Both things are both things are valid, but whichever suits you. So I will say perpendicular distance to point P. Okay, what do you mean by perpendicular distance? So here if I observe that I have a point P here, right? So the distance is this r, but actually the magnetic field will be only be contributed due to the perpendicular distance and not due to this parallel distance. Okay, magnetic field will be contributed due to this parallel distance, only due to the perpendicular distance magnetic field will be contributed. I will explain this later on, but just have this in your idea, have this in your mind. Okay, so here for this, right, I am mainly interested in calculating the magnitude because they haven't mentioned the coordinates of this particular wire. So for this it was easy. Okay, but this is difficult, so I will not go into that right now. That will just waste our time. So I'll just directly say what will be the magnitude of the particular thing and whether it will come out of the screen or come into the screen. That much I can comment about. Exact direction I cannot comment about the magnetic field, but I can comment briefly about whether it will come out of the screen or come into the screen. Okay, that much I can comment. So that much I will do. So first of all, I will compute the magnitude of the magnetic field. Okay, what is the magnitude of the magnetic field? Magnitude of the magnetic field dB will be mu naught free space by 4 pi into I dl sin theta by r square. Okay, I have already taken into account the sin theta. I have already taken into account the perpendicular length, right? This I have already taken into account the perpendicular length because this length, okay, this has two components. One is this cos theta component, like this is r, right, and this is l. Okay, so if I do l cos theta, it will be along this line, and if I do l sin theta, it will be along this line. So the current is only due to the perpendicular component and not due to the parallel component. So that's why l sin theta comes. I hope you understand that thing now. That's why l sin theta comes, because this, right, if I do l cos theta, theta is this. If I do dl cos theta will be along and dl sin theta will be perpendicular, right? And this will not contribute any magnetic field, only this perpendicular component will contribute magnetic field. That's why there is a dl sin theta over here. I hope you understand this thing. So I'll just write there also that this sin theta is due to what? Just right here. Why is there a sin theta, right? So why is there a sin theta? I'll just explain it a bit. Because just here I have a point P, okay, and this is a wire and this is the current direction, right? So currently this has two components. One, like this is the theta, this is the theta, and this is the current element, right? So this element will have one component along this end and we'll have other component perpendicular to this. Okay, so obviously this will not contribute, no contribution magnetic field, but this parallel component, right, it will contribute. So that's why this sin theta terms comes. Okay, just I trust me, none of the educators will actually explain this much. They will just directly tell you the formula. Okay, I will show you the formula. They will directly tell you that formula. They will not even explain these things. Okay, they will not start with this because I know what like I've seen the teaching, so they don't explain. So, but I want you to explain everything. I want you to explain everything. Why? Because you should know the reasoning behind what is happening. But then only you'll be able to solve the gate question. Because in gate question they test your reasoning ability as well. Okay, not just simple formulas. So here this will be ideal sin theta, and sin theta, what is sin theta? Sin theta is sin 37, so it will be 10 raised to power minus 7 into I is 50 ampere second, dl is 1 centimeter, that is 10 raised to power minus 2 into sin theta. Sin theta is this is how much? Sin 37 is 3 by 5, correct? Sin 37 is 3 by 5 simply, and divided by the 1 square. Okay, so this will be simply 5 will get cancelled. This will be 30 nanotesla. This will be the magnitude. Actually direction I will not comment, but what I can comment is this will come out of the screen, right? This will come out of the screen. This will not go into the screen. Why? Because if I just curl my fingers, it is coming towards me. So what will you show here? Will it be a dot or a cross? It will be simply a dot, right? Because it is coming out towards, a arrow is coming towards me. I can just show the tip of the arrow. Now there are few terms that you should know. Okay, these terms will be used later on. I just wanted to explain few terms. Is that this is the first term, and this is the most important term. Other terms are not that important. One term is surface current density. Surface current density is the amount of current per unit length on a material's surface. So if I have a current flowing, okay, if I have a current flowing I, okay, but I don't want to comment about I want to comment the amount of current flowing per unit length, okay, on that particular surface. Surface is constant. The amount of current that will flow on that surface per unit length is known as surface current density. Okay, just don't get confused. This is per unit length and not area. Per unit length and not area, because this surface is fixed. The current is flowing on the surface. Whenever a current flows on the surface, then we comment about surface current density. Surface has already been fixed, so the whole current is flowing through this surface, but I wanted to take a small length dl through this section dl. Okay, and what is the amount of current that is flowing through this section dl? That will be equals to some value I, and if I integrate this k in dl, I will get that value I. Okay, that is the thing. And if you want to define the surface current density, okay, what you can do is you can equate this with the charge present on this surface rho s times the velocity. Okay, velocity of those charges. If you do this, then you will get your surface current density. That's it. And and what is a surface current element? So like this is surface current density. Okay, this is surface charge density, and this is the velocity of the charges. Okay, velocity simple velocity. Okay, so here if you observe that if I want to write a surface current element, ideal was a surface it was a line current element. Okay, ideal was a current element, but it was a line current element. So a surface current element will be defined like this: surface current element is equals to k dA. Now this dA doesn't have any vector quantity. K already is a vector quantity, and like this is just a definition. That's it. Okay, the current that passes through a length, okay, small length dl. That's the definition. That's it. Okay, so there is another term known as volume current density, because line current density we already know, that is ideal. Volume current density is the current that for a particular volume, the current that passes through a area, crosses area. So I have a area dA, and the amount of current that will cross through this area divided by like per unit area, the amount of current crosses per unit area is known as the volume current density. Okay, remember it is although it is defined for a volume, but definition is divided by area. Just don't get confused by that. Volume current density is the amount of current flowing per unit area on a material's surface. Okay, I hope you understand this thing. So this thing is the volume current density. Again, what is rho v? Rho v is the volume charge density, if you remember. Okay, volume charge density, and v is the simply velocity. Okay, v is the simply velocity. So these are the few things. And if you want to write a volume current element, how can you write a volume current element? It will be simply G J dV. J dot dV. This will be a volume, not dot, simply J dV, volume current element, just same as surface current element, and it is a volume current element. These are few definitions that we should know. This will be handy later on. Okay, now like I've already told you about the vector format of Biot-Savart's law. Why I have divided by the like here magnitude. I haven't divided by magnitude because this is already in the unit vector condition. Now in many cases this dV can come as a line integral. For what? It will come as a line integral when this is a current element. Okay, you have to do line integral to find out the whole magnetic field when it is a current current element, line current element. Okay, line current element. This is a line current element. Now your Biot-Savart's law can be in other forms as well. What is the other form? If it is in surface current element, if K is given, then you have to do this. Okay, if it is in surface current element, just here, then you have to do the area integration, right? Double integration. You have to do the surface integration. Here you have to do the line integral to find out the magnetic field, but here you have to do the surface integration. If what is given, if surface current element is given. Okay. Next, if volume current element is given, JDV. If volume current element is given, you have to do triple integration, that is the volume integral, to find out the magnetic flux density. Okay, I'm just showing you the different forms of Biot-Savart law, so that you don't get scared once you see a new form. Okay, just the same thing written separately for different types of current element. Okay, I hope you understand this thing. Now here again I'm focusing more on the direction of the current element, because if I observe, if I have a current that is flowing like this from bottom to top, and if I want to measure if I want to see the direction, what on the right hand side, all the magnetic field will be pointing inwards and all the magnetic field will be pointing outwards. So is there any particular relationship? Is there a particular formula for magnetic field? There is, obviously, we'll derive that. So just how do you find out the direction? Just one more time, point your thumb towards the current element and then just curl your fingers. So on the right hand side, I see all the magnetic field will be going inwards, the plane, and on the left hand side, all the magnetic field will be coming outwards. And if I curl this thing, they are covering a total circle. So again, that fundamental property of magnetic field is what? There is no source or sink. It always is in a loop. It is always is in a closed loop. Okay, so that's why the divergence of magnetic field will be 0. So that law is also followed here. Okay, so now we will do few derivations with the help of Biot-Savart law. We will actually derive the magnetic field due to a current carrying wire. So I have told you that if a current is flowing through a wire, magnetic field is getting produced, but how much is the magnitude of the magnetic field, that I will derive here. And directions, obviously you can do it with the help of right hand rule. Okay, so I will just take a small element. So there is this interface. Okay, this configuration is there, this R is there, this is not at the center. Okay, not at the center. So there is angle alpha beta between these two, and I have to find out the current through whole of this element, current element. Okay, this big element I. So how do I find out? So first of all, I will just take a small element. Okay, small line current element dx. Okay, dx. If I take a small line current element dx, the distance from this dx will be what? This is very small. Okay, it will be almost equals to r dash. And if it is almost equals to r dash, what angle I used to take? The angle between the current element and the line joining the point and this current element. So this is the angle. For now, let's name this angle as theta. So this angle is theta. So due to the small current element, can you write the magnetic field? Please write me the magnitude. I don't want the direction now. I just want to write the magnitude. So what will be the magnitude of the magnetic field? dB equals to, I will assume this is some magnetic permeability is mu by 4 pi into IDL now, this will be IDX, because this small element is of length dx. IDX into the angle, that is sine theta, and obviously the distance between these things, r dash whole square. Okay, so here what is variable? Basically here I can see many things are variable. Here I can see my x is also variable. Okay, the length. What are the variables? X, r dash is variable, theta is variable, right? All these three things are variable, so things are become very complicated for me. Okay, so I will obviously reduce my variables to one single variable, okay, so that I can easily simplify this integration. Okay, so I will apply few tricks. So if this angle is theta, then this angle will be what? This angle will be pi minus theta, correct? If this angle is pi minus theta, then one relationship I will use. What is the relationship? That relationship is that I know my sine pi minus theta is equals to sine theta. Okay, this thing I will use. What is my sine theta actually? What is my sine theta? So how do I comment about sine theta? So if I observe, can I comment about? I can comment about sine pi minus theta. Okay, I can comment about sine pi minus theta. What is sine pi minus theta? This is the hypotenuse and this is the altitude. Sine pi minus theta will be what? This will be equals to what? This will be altitude by hypotenuse, r upon r dash. This is equals to what? R upon r dash, and this is simply equals to sine theta. This is equals to my sine theta, right? And in the formula, I have sine theta only. So I can simply, I have reduced one variable, theta I have reduced, okay? So now my formula becomes what? Now my formula becomes dB equals to mu upon 4 pi I is constant obviously, dx, and this sine theta has been reduced to r upon r dash. So this actually becomes r by r dash whole cube, and this r is what? This r is the perpendicular distance, right, from that particular element. Okay, so or r is the distance from the point P to the particular perpendicular distance. R is the perpendicular distance. Okay, so and it is constant. Perpendicular distance will not change, it is constant. Okay, so now what I can say, what is r dash? Can I comment about r dash as well? Can I comment about r dash as well? R dash is what? This distance is x, right? I have assumed that I am flowing along this distance x. Okay, I haven't told there that I am going along this distance x. So if this is x and if this is r, can I write down r dash with the help of Pythagoras? Yes. So what will be my r dash? R dash will be simply x square plus small r square whole under root. Okay, so okay, this is already here, sorry for taking this page. So what I can say is basically I can further rewrite this. What I can rewrite this can be rewritten to this thing. Just copy this thing. That your dB, magnitude of dB, okay, not vector format, just in scalar format, dB becomes what? dB is not mu naught actually, mu upon 4 pi idx. R is constant, correct, divided by x square plus r square under root 3 by 2. Now this is the case, right? This is the case, and now I'm ready to complete my integration. Why did I choose dx? Because I had to basically integrate. Just hold on. I have to simply integrate throughout this length, right, from here to here. So x equals to 0 to x equals to L. So this particular area is x equals to 0, x equals to L. But it's not that simple, okay, because this integration is very difficult. I cannot simply integrate with respect to x. So I have to do few substitutions. What substitution I will do? So I will use the simple formula tan theta. Okay, what I can observe, the relationship between x and r. What is the relationship between x and r? Okay, I will write that in terms of theta. So do I have the diagram here? No, I don't have the diagram. So if I observe here, x is this height and this is pi minus theta, right? So what is simply x by r? What is x by r? Or what is r by x? R by x will be tan of pi minus theta, right? I hope you know simple trigonometry. So r by x will be tan of pi minus theta. This I think you can figure this one out simply. If you are not able to, you have to do it by yourself. Okay. Now what is tan of pi minus theta actually? Tan of pi minus theta, if you tend to forget this thing, is sine of pi minus theta divided by cos of pi minus theta. Now, yeah, sin pi minus theta is sin theta itself, but cos of pi minus theta is actually minus cos of theta. So overall this becomes r by x becomes minus cot of theta. But you said you wanted to write in terms of r, right? So like what is r equals to? R equals to no, I wanted to write in terms of x. Okay, so r is equals to, just hold on, yeah, sorry, x is equals to what? X is equals to simply hold on a second, am I doing something wrong here? So this is tan theta, sorry, this is tan theta only, right? Minus tan theta. So what is x equals to? So my x is equals to simply minus r cos theta. Now if I take the derivative with respect to theta on both sides, r is a constant, so r will be outside, and this will become minus r cos theta. Differentiation is what? Cosec minus of cosec theta or minus of cosec square theta. This one is the only differentiation, right? If you remember, so this one will come out to be d theta is here obviously. This one will come out to be dx is equals to r cosec square theta d theta. So this will be the variable that I will replace here. Okay, so this is, I'm ready to do my integration now. So what I will do, I can write my dB. I will write everything in terms of theta now. So I will replace dx. Okay, this was equals to what? This was equals to my mu by 4 pi just hold on, mu by 4 pi into idl, and dx has been changed to d theta now. What is it? It is simply like r was there separately previously. Okay, and this has become dx has become r cosec square theta d theta divided by, now what is r square plus x square? R square plus x square will be what now? So r square plus x square will be simply equals to r square plus r square cot square theta. So this will be r square 1 plus cot square theta. This will be equals to r square cosec square theta. Okay, now what is happening over here is that this is r square cosec square theta, right? But there is an under root as well to it. So this will come out to be this will come out to be this. Here it is r square cosec square theta whole under root, right? Why? Because if you observe here, it was 3 by 2, sorry, it was 3 by 2 actually. So it will be 3 by 2 whole not under root, 3 by 2 raised to the power 3 by 2. Yeah, sorry for the sneezing, I had a cough basically. So now overall what is this becomes? This becomes overall 1 by cosec theta. Okay, and obviously d theta is here, right? D theta is here. So overall what I will do, I will just write this thing that this will be dB. I will integrate from b equals to 0 if I am at this particular point, right? I don't have any relative field because there is no current element after this, right? To b equals to full b, because all of them will be summed, equals to mu by 4 pi. I will be at the top and all the other things, right, will be just inside because theta is variable this time. This will become sin theta d theta because 1 by cosec is simply sin theta. Okay, so but what are the limits of theta? So what is theta basically? What is theta? So here I can observe that theta definition, what is the definition of theta? Theta definition is the angle between this current element ideal and this r vector, right, towards the point, going towards the point. So angle between ideal and r vector. So here the angle is alpha, so I will start from alpha. But here what is the angle? Here what is the angle? Is the angle beta? No, the angle is not beta. Why is the angle not beta? Because this is the current element and this is the r vector, right? So this is the angle. What is this angle equals to? This angle is equals to pi minus beta. Okay, this angle will be equals to pi minus beta. So I will go from alpha to pi minus beta. Trust me, don't worry, all this is not that important. If you couldn't understand the derivation as well, not important, just the formula is important. Okay, that I will tell you, and that will be easier for you to remember as well. But if you understand the derivation, right, then it will be easier for you to remember the formula, and it's good to understand everything. So this will go from alpha to pi minus beta. And what is the integration of sine theta? The integration of sine theta is simply minus of cos theta. It is minus of cos theta. I will flip the limits then. So what I will do, this will be mu I by 4 pi cos theta. Limits will be flipped because negative sign I am taking inside. I will not teach you basic integration. This much you know. So this will be pi minus beta to alpha. Okay. Now, can I put these values here? So I know cos of pi minus theta is minus cos theta. So this will become okay, did I do anything wrong here? Yeah, cos alpha. Yeah, this is the correct only, cos alpha cos beta. So what will come? This will be cos alpha plus cos beta, because it was cos alpha minus of cos pi minus beta, and cos pi minus beta in itself is minus cos beta. So my final result will come out to be this. Okay, and it will be in Arrow-Curve direction if you are taking cylindrical coordinates. So that's how I get the direction, but direction you will be able to do, but main thing is this thing. This is one beautiful expression that we get. And okay, did I miss anything here? This is r, just hold on a second. Okay, sorry, so this won't be r square actually, this will be simply r only. So actually what will happen, there will be a r at the bottom. I missed that thing. There will be a r at the bottom. So that makes sense as well. As I move further away from the wire, the magnetic field intensity should reduce, and that is exactly what is happening over here, right? The magnetic field intensity is reducing. So what I can say is here the main thing is you have to remember this formula. That's it. This formula is the most important thing, and I have seen many educators teach different cases for this. You don't have to remember any cases, just simply remembering this formula is enough. Okay, just remember this. It will be the magnetic field at a distance, perpendicular distance of r. So this r is the perpendicular distance from the current carrying element. Okay, it will be equals to mu I by 4 pi r. R is the perpendicular distance into cos alpha. Alpha is what? Alpha is the angle between the current element and this point, and it is the interior angle, right? Interior angle of this triangle's form. This particular triangle form, it is the angles of the two sides which is connected with the ideal element. This much you have to remember. You have to remember what is alpha and what is beta. Alpha and beta are angles subtended by ends of wire at P. The definition for theta was something else. Okay, the definition of theta was something else. Now forget that. Just remember this. What is alpha and beta? Alpha beta is the angle subtended by ends of the wire by the point P. Now many in books and stuff, other things as well, I have seen that they give you a formula with respect to theta 1 and theta 2. That is with respect to this normal theta 1 and theta 2. I will highly recommend, don't remember that, but if someone is already have studied previously and they are revising, so they may find bit of resemblance with that particular angle, with that particular formula. So I will recommend you forget that formula. Just remember this new formula, cos alpha plus cos beta mu I upon 4 pi r, and this is very important formula, and this will be used everywhere. Okay, so just remember one thing, that this r is the perpendicular distance about this wire. What is the perpendicular distance? If a point P is lying here, I will not find out this distance, I will find out this distance. This is the perpendicular distance. I have to understand this point. So let's take a few edge cases. Okay, so we will do edge cases. Basically we will derive the formulas for a few symmetric cases. So if I have a infinite wire, okay, infinite wire, okay, infinitely like the length of the wire is infinity, from minus infinity to plus infinity. It is infinitely straight wire, it is carrying current I. Due to that, what will be the magnetic field? So what will happen is that this thing, right, if I choose this thing, what will happen? This angle will keep on increasing, right? This is going towards infinity, and this is also going towards infinity, correct? If I observe, this angle is also going towards infinity. So where are my beta is going? Where is my beta going? So if you observe that angle here was something big, if I would have done angle here beta, again here the angle has reduced, again here the angle has further reduced. So beta is going towards 0. But where is alpha going towards? Alpha is also going towards 0. Okay, why? Because if this angle is getting increased, right? Initially this was the angle, now this is the angle, now this is the angle, alpha is reducing, right? So I can, like, from observation I can say beta and alpha are reducing. So at infinity what will happen? They will go towards 0. They will basically go towards 0. So beta and alpha will go towards 0. Now if beta and alpha are 0, then what will my magnetic field expression become? It will be mu I upon beta and alpha 0, right? So cos 0 is 1, actually not 0, plus 1 divided by what? 4 pi r. So this actually becomes mu naught I by 2 pi r, and this is also a very, very important expression in the a phi cap direction. This also you should know. Okay, but do you need to remember? No need to remember, just remember the main formulae and all other expression you will derive from this. Okay, all other edge cases I will tell you how to derive. Okay, so I hope you got this point. Now there is another edge case. What is the other edge case? Other edge case is due to a semi-infinite watt. So like here I've just shown you the characteristics of this magnetic field. Okay, this is the line current carrying wire. If I'm on the right hand side, it will be inwards, going inwards the screen. If I'm on the left hand side, it will be outwards. This is the direction of magnetic field as it is showing. Also one more thing that you can observe, if I'm very close to the current carrying wire, the magnetic field lines are very dense. If I'm very further away from the wires, the magnetic field lines also, the density of the magnetic field lines also reduces. As intuitive, right? It's intuitive, because the further I will move from the wire, the effect of that wire will reduce. Basically the magnetic field due to that wire will simply reduce. Okay, so this is the relationship for a magnetic field, magnitude of the magnetic field if I am moving along the R0 direction, right? R0 direction, basically along the perpendicular direction. So it will be just like a rectangular hyperbola. So it will just be like a rectangular okay. Why is it called rectangular hyperbola? Because P varies inversely to 1 by r. That's the name of this particular function, rectangular hyperbola, right? So there is another edge case. What is the other edge case? Other edge case is magnetic field due to current carrying semi-infinite wire. Okay, if it is semi-infinite, like it is finite from one end but infinity to the other end, then what will happen? Then things will be a bit different, because if I'm lying at this edge, then the magnetic field will be something else. If I'm lying here, right, then magnetic field due to this will be some angle due to this alpha, and this angle will keep on reducing. Again, this angle, if I'm lying at this point, right, at this point, then what is this angle? This angle is simply 90, right? So one of the angle alpha is simply 90. Okay, what about beta? Again, for beta, right, same thing will happen. Beta will keep on reducing. Okay, just hold on, let me just, beta will keep on reducing until what? Until beta goes to 0. Okay, so beta roughly equals to 0. So this time it will not be exactly mu naught by 2 pi r. So it will be B will be mu by I 4 pi r. R is the perpendicular distance into cos of 90. For one of them it will be 0, alpha is 0, plus cos of beta, cos of 0. So it will become mu I by 4 pi r, and obviously the direction is a phi cap. Okay, a phi cap direction. So that is the case over here. So these are few edge cases. I hope you understood these things. Now only with solving questions we will be able to understand. Okay, so let's solve few basic questions. Let's solve this question. Okay, let's solve this question. I will solve few questions and give few questions I will give you as homeworks for the next lecture. Okay, so let's solve this basic question. So here, what will be the magnetic field at P? Okay, so I know the basic formula, right? What is the basic formula? This is a infinite wire. If this is infinite wire, I know the basic thing that in case of one magnetic field will be simply, you can either write the cos alpha plus cos beta and then there put alpha and beta equal to 0, or directly write here mu I by 2 pi r, right? It was for infinite wire on both ends, it is 2 pi r e phi cap direction. So mu, as nothing is given, I will just assume that it is free space. So this will be 10 raised to power 4 pi into 10 raised to power minus 7 divided by 2 pi into I is 10 divided by the perpendicular distance. What is the perpendicular distance? Sorry, it is simply 10, right? So perpendicular distance is simply 10 centimeters. Remember, this is in centimeters, so I have to write this in meters actually. 10 raised to power minus 2, and E rho cap will be obviously there, right? So this one will come out to be 2 into 10 gets 10 raised to power 2, so 10 raised to power minus 5 E rho cap. This I can write as 20 micro Tesla. Okay, so this will be the answer, 20 micro Tesla along the direction E rho cap. That's it, right? Or if you want to write in terms of the plane, it is going away into the plane, right? Going away from me, it is going into the plane. So direction you can show with cross or dot, it will be cross. Okay, part 2, second part also you can solve, right? Second part also you can solve. So this is same only, just the direction has changed. It is also going into the plane here. If I observe, it is also going into the plane only, but this time this will be my z axis. Okay, this was z axis previously, now this is my z axis, right? But if they have specifically mentioned here z axis, then you have to solve it according to that. Okay, so then that is the important point that I want to talk about. So you have to choose your aero cap. So they have to define this where this is wire placed as well. So this coordinate system is bit right now. This is not to get confused with. I will remove it because they have to define where this wire is placed, and then only you will be able to identify the direction. Okay, so if nothing is mentioned, you will just assume a standard difference. So I assume this has z axis and I solve along to that. So for the part 2, it will be same only. It will not, there will be no difference because this has perpendicular distance of 10 centimeter, current is 10. Just it is again going into the plane, but like this. It is going like this. Here it was going like this. Okay, so I hope you get the difference. So this will be the same thing only, mu I by 2 pi r a phi, but a phi reference has changed. Here important point is reference has changed. I have chosen the reference. Okay, mostly they will ask about that going into the plane or coming out of the plane. That's it, that's the main direction they will ask. Okay, so this will be the same thing only, right? 20 micro Tesla a phi cap, and this is also going into the plane, right? This is also going into the plane. If the current direction, let's say, was in this direction, so I'll just change the direction just for the fun of it. So if I change the direction, right, in this direction, now tell me what is the current direction. Now the direction will be like point your fingers towards the current and do it like this. So what I'm observing, that the current direction is something like this. Okay, coming out of the plane. If I am at this point, it will be coming out of the plane. I will see a arrow towards me. I'm seeing the fingers are coming towards me. So obviously this is coming out of the plane. So this will be simply okay, this will be simply dot because it is coming out. I am just seeing an arrow towards me. So I will understand this point. So with the help of this concept, can you solve this? Now here direction is important because this question has proper direction mentioned, everything is mentioned, right? So solve this question. I will give you this as homework. Okay, and this question also will give you as homework only. Just tell me, you don't need to talk about direction, just tell me whether it will be going into the plane or coming outside the plane. Okay, this is for a semi-infinite, or is this? No, this is not for a semi-infinite. This is just for a finite like carrying wire. This is for a semi-infinite. Okay, now here exactly the point is not present along the other end, right? One of the ends, it is present somewhere in between. So for this, what will be the equations, that all those things I wanted to derive? I will just remove the axis now. Now here one interesting point that I want to go, I'm just giving all of this as homework. Can you tell me what will be the electric field at this point P due to, like, there are two sections, there are two semi-infinite wires. Can you tell me what is the electric field due to this infinite wire? Okay, semi-infinite wire. Okay, tell me that, put in the comments below. Tell me what is the electric field contributed due to this particular semi-infinite wire at this point P. Okay, you can talk about that. We'll discuss all these things in the next lecture. We'll discuss all these things in the next lecture. You can pause the video, like few hints I'm giving you. It's very easy to find out. Okay, so yeah, I am giving all questions as homework. This also is homework, and this question is also homework. These are all good questions. Okay, you can solve all this. So, like, these are all 3D figures as well. So here totally Cartesian coordinate system is given. You can pause the like, take a screenshot, and this is at the end. We will derive this, just simple superposition. We're just using simple superposition, and I will derive this in front of you in the next lecture. What will be the expression for electric field at this point, like for the 10th question. Okay, so yeah, that's basically it for this video. And in the next lecture I will solve all this. I will derive the expression for these type of shapes, regular polygons, what will be the magnetic field, and we will derive for like circular coil as well, what is the magnetic field due to a circular coil. Thank you for watching and happy learning.